In this lesson, you are going to define the process of mapping continuous random variables, identify how to map continuous random variables, and recognize the essence of mapping continuous random variables. In our last session, we learned about investigating multivariate random Gaussian. We compared the multivariate Gaussian and the univariate Gaussian. We said that because the coefficient is negative, the parabola is pointing downwards, and this is true for both Gaussians. We pointed out that the concept of covariance matrix is very important in multivariate Gaussian because when we properly understand it, we can clearly and directly summarize all pairs of variables. If you missed lesson number 12, the link is given in the description below. Understanding this lesson becomes meaningful if you understand lesson number 12. After understanding some of the important concepts, now we will study how to map continuous random variables. So we actually had learned how to map certain variables in our past lessons. So the link to that lesson is given in the description below for you to be able to understand this one properly if you haven't studied or watched our previous lessons. So I would provide the descriptions to the playlist itself so you could just follow through what we're going to go or what we will be doing for the next sessions and what we did for the past lessons so that you will be able to understand what's going on in this session. So now let's try to look at this map. So we have here x is defined by point R to R, and this one or this corresponds to this mathematical expression, and this means the probability measure of x is defined by the point from R to this point, which is 0 and 1. So what do we mean by this? What does this mean? So first, let us remember that we must make a separation between the definition of the function and the target items of the function. So here in our case, this is actually the function. And the function tells us everything around the data, all points in the data. So when this is the data, so all the points that you can see in here are included in this function. And now, what about this one? Maybe you would ask me that. What's the relation of this to this? So as we've said, this one corresponds to this. Now it's like this. So this describes the target function. And what do we mean by that? So when we have this circle, for example, sorry for my drawing, just think this one is a perfect circle. So it means that our target function is this. So only the points that are included in the small circle inside this big circle are considered to be the target values for this function. So we do not consider these points outside the small circle, but only the points in this circle. So basically, this is the meaning of this. So now let's concretely understand this concept properly by answering this question. So our question is this: what is the probability that a uniformly distributed random variable on the unit interval takes a value less than 1 or less than 1/2? So let's make a drawing. Sorry for my line is not always perfect. Just let's think that this line is perfect. And remember before we've been drawing this one. So for example, this is our line, and this is 1, and then this is 2. But the problem is that we're going to look for a probability that something is going to happen less than 1/2. So this is 1/2. Okay, so this is the origin. This is 0. And what we're going to consider is that only this point, not above it, but only from 0 to 1/2. Okay, so again, let me repeat the problem. So what is the probability that a uniformly distributed random variable on the unit interval takes values less than 1/2? So remember this, we are considering a uniform distribution. Okay, so using the structure that we have defined earlier, we can write the problem statement this way. So this problem can be written as this. Okay, so we define x as 0 and 1 to 0 and 1. So it means this is the total points that can be found in the function. Okay, but then we are not concerned with every point in the whole function, but we only, like this one, we only focus ourselves on what's in the subset in a certain function inside the main function. So what is that? So here we have the probability measure of x is defined as 0, 1 to 0, 1. Okay, so again, this defines the function, and this corresponds to the target, which is this one. Okay, so again, remember that we are looking for the values 1/2. Don't forget that we are looking for the value 1/2, and this means the interval 0 to 1/2. So our problem is a case of a uniform random variable, and this can be computed using this integral. Okay, so by this time we're going to use the integral, how to compute this, and to arrive at the value of 1/2. What's the probability? Okay, so let's do this one. So this is our equation to solve this. Okay, so the probability of x defined by the interval from 0 to 1/2 is equal to the probability of the interval that is from 0 to 1/2. I forgot. Okay, so this can be written in this integral. Okay, so we have from point 0 to 1/2 dx, this is equal to 1/2. So if we're going to compute this, then the result would still be 1/2. That the probability of happening of a certain event from 0 to 1/2 is 1/2. Okay, so you can actually compute this one at home. If this one is not correct, you can just comment below. But for you to be able to prove that this one is really 1/2, you may compute this one. Okay, so if you have some questions in the computation, you can just comment below. And then what's the intuition behind this? What's the meaning? So this integral reflects also the subset. The measure of any dx interval is equal to dx. So remember that this is defined by the uniform random variable. So in the statement, we can actually include both the function and the target values. So as you could see here, in our first statement, we could not find in our statement here the subset or the target function. So this one represents the function, which is the main function. Now, how are we going to integrate the target function, which can be x? So we have here, how to do that is like this. So of course we are defining here the interval from 0 to 1/2, and then what we do is that we are going to integrate the value of the interval or the target interval. And to do that, so we have this from 0 to 1/2, then this is our target. So you can actually write that using just only one letter, like x. Usually we write x. Okay, then this one is the function interval, and then this is equal to 1/2. What is the significance of knowing this? In many situations, values can be countless within a certain interval, like when you are asked, how long can you run for 10 minutes? The distance you travel may vary every time you try. So in this case, mapping a continuous random value can properly mimic the underlying reality. After all being said and done, let's try this. How do you map a continuous random variable? And why do we have to map a continuous random variable? Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.